So I will start off with the world of quantum dots, and I'm lucky to follow Mark, who gave a very good overview of the electron. Of course, we are dealing with the atom and the electron, and obviously photons, which is the foundation of quantum. Now, just to follow up maybe on Jody as well, who spoke about our end goal, which is the establishment or the commercialization of research and more on the technological and innovation side. I was doing some research last night and back to Mark as well, and I came across a colleague who started the nanotechnology initiative many years ago in 2000, around about 2000. And he was a professor at UCT, and many may know of him. His name is David Britton, with his colleague Mahit, and they had this wonderful idea of printed electronics, where they would take silicon and screen print them onto circuits, and that was in around about 2002, and that project went on for many years. And just looking at the history, and David was talking about it, and it's still carrying on, and they're still trying to get the company going, but it required a lot of effort, almost 20 years of research. So the take-home message here is these technologies do take time. And David and Mahit, from my experience with them, two of the most intelligent people that I've met, and they've been working on this project and working on this idea for almost 20 years, and still trying to get something out of it. So today I'll speak about the quantum dots, and the title is Colorful World of Quantum Dots. So can I move my next slide? I'm moving. Okay. So I'm at the University of Zululand, which is north of Durban. Many people get confused with KwaZulu-Natal and University of KwaZulu-Natal, but this is not KwaZulu-Natal. This is Zululand, which is a different university independent of KwaZulu-Natal, 200 kilometers north of Durban, across the Tugela. It's a rural campus. We now have two campuses, one at Richards Bay and one at Ongoye, the old campus, and it's obviously growing in terms of infrastructure. We have now have an engineering department, and we've had a science faculty of science for as long as the university was established. Now, in terms of quantum and nano, how do two work? And that's the aim of my talk is to show you how we can bridge the gap between nano and quantum, and look at the properties that nanomaterials give us and how they influence the uh, application of these in quantum technologies. And I'll give you one example that a project that we are working on. And my colleague Bartus will give you more details of that, but I'll set the background or the stage for him to explain what we're trying to achieve. So we're looking at materials. When we talk about nanotechnology, nanomaterials, it's normally between 1 and 100 nanometers. But for quantum dots and the materials that we are trying to make is much smaller than that, sub 10 nanometers. So we're looking at many, 5 nanometer particles. And this field is obviously made possible by the electron microscope or microscopy. So in 1982, the scanning tunneling microscope was discovered or invented, and then we had the atomic force microscope. And again, Mark spoke about lithography, where you could move atoms and study them. So it's a very multidisciplinary field involving physics, chemistry, and biology, engineering, and so it can't be put into a box in one area. So we are working with, or we do work with colleagues from different areas of science. Now, just a small history. Uh, so nanotechnology can be traced to a lecture by Richard Feynman, the famous physicist, where he spoke about manipulation of matter at the nanoscale, and he gave two challenges, which we both both achieved, and you could arrange atoms the way we want, and to do chemical synthesis by mechanical manipulation. So this gave the birth to the idea of nanotechnology. Of course, this was proven almost in the 1800s by Faraday, Michael Faraday, who made gold colloids. And so these uh, his uh, his uh, solution, or the colloidal solution of the gold, is still in the British museum, and it was, if you dig up or you do some research, and you can see they've been re working of the work that he's done, an explanation of it, and some studies, new studies on the material that he's made many years ago. Of course, it goes back further to the Lycurgus cup in 14, 4 AD by the Chinese, and so this cup was made of gold colloids, and when you expose it to the sunlight, it changes color, and that's purely due to the size of the gold particles in the cup. Now, why are we so fascinated about quantum dots, and in particular the colors of the material and the emission of light that's given off? Well, this is the properties can be explained using this model where we have, a valence band. This is a semiconductor sketch. So in a semiconductor, or any material, it can be a semiconductor or metal or insulator, you have a band gap. And for semiconductors at 0 Kelvin, you have the electrons that sit on the valence band, and you have an empty conduction band. And then you can then, above 0 Kelvin, you can excite, you provide energy, and you can excite the electron from the valence band to the conduction band. And when you do that, you have what is known as a positive hole that's left behind in the valence band, and you have the electron now sitting in the conduction band. Of course, these electrons now form what is known as a exciton, where it's a bound electron hole pair, and it is associated with an electron trapped in a localized state in band gap. Now, the amount of energy that's required to excite the electron from the valence band to the conduction band gives you the band gap energy. Now, now in quantum dots, or in nanomaterials, quantum materials, quantum dots. Now this exciton, the radius between the hole and the electron, is the size of your material is now equal or less than the radius between the uh, hole and the electron. And when that happens, you have an amazing phenomenon called a quantum size effect, where you have now an increase in the band gap of uh, the material. And that is shown in the next slide. You can see in a normal material, the bulk material, you have a band gap. But when you have a quantum dot, or a material that's uh, very small, between 0 to 5 or 0 to 10 nanometers, you have an increase in the band gap. And you can see as you decrease or increase the band gap, you have a change in size. So increase in size, and decrease, and a change in color. So the emission that's given off is directly related to the decrease in the size and increase in the band gap. So these are the fascinating properties of quantum dots. Now, I can explain that further. Why do we get an increase in the band gap, and why do we get different colors, which I'll explain in the next slide. So here you see this electron hole is now in what is known as, or it can be treated as, a particle in a box model. And if you see the dimensions of the box being the dimension of the particle, and as you increase or decrease the size of the particle, the absorption increases, your energy increases. So you can imagine something being squeezed in the box, and you make the box smaller, and you have an increase in the amplitude of the absorption function. So that gives you very simply why the band gap increases. So you then have your electrons and your holes, and I'll explain further, yeah, in this slide. So what happens then when the electron goes from the valence band to the conduction band? Obviously, it doesn't stay long. It has a lifetime, and that lifetime then it goes back to the uh, comes back to the ground state, which is the valence band, and it does this. And when it does come back, it gives off gives off a photon, right? In your radiative recombination process. So that's what we are interested in. In the quantum technology is the photon. So quantum dots are sources of photons. Now, here you have recombination, you have band-to-band recombination, or you can have inter recombination via trap states. So we have trap, the electron can go up and it can come down and it can get trapped. And the trap, uh, what traps the electron are defects. And so what for chemists, what is important is that these defects can be are related to the surface of the quantum dot. And the surface of the quantum dot has to be passivated by organic ligands or capping groups, and that prevents any defect emission. So what we really want is clean emission or band-to-band recombination, giving you a good quality photon of light. So we can measure the quality of the light that's given off using for um, uh, PL spectroscopy, and you can see, yeah, this is a good image showing you different colors of quantum dots and related to the uh, PL spectrum, right? So by purely by engineering the size, you can get different emission properties. And that's related by this equation, which is the Brass equation, where the energy that's given off is directly inversely proportional to the size. So this equation uh, by Louis Brass, who won the Nobel Prize, which I'll talk about a bit later, uh, it relates the energy to uh, the size of the material. And we can show that in the work that we've made. So cadmium selenide quantum dots are the sort of uh, one of the first materials that was widely studied. It was known as the kind of Cinderella material, having promising properties. And so a lot of the early work was done on cadmium selenide quantum dots. And you'll see here at 100 degrees, you can get emission, photoluminescence at three, which is 515 nanometers. And you'll see in the absorption spectrum, it has very distinct features in terms of excitonic features. So these excitonic features are very indicative of small particles. And then if you increase the temperature, from 100 to 150 and 250, you can see the emission moves more red. So it's from 515, it goes to 688, right? And you see the excitonic features sort of flatten out. You don't see very distinct excitonic features. And then you can see them obviously with the electron microscope. You can view the particles. They are very small and very distinct. And you can see the color changes, from a light to a darker color, purely based on size. Now, how is that applied? It's applied in quantum dot LED TV. So these are already in the marketplace, where they use the phenomenon of what I've explained to replace materials now using quantum dots in the as which function as LEDs. So again, just a brief slide on surface ligand. So as I said, you need to not have any defects because you want emission at the band edge, and you normally use organic shells that will make sure that they passivate the surface, and they are more importantly also prevent any aggregation. So then you can get this is an example of a quantum dot, 4 to 5 nanometers, maybe about 3,000 atoms, and passivated. You can't see the halo, but around the dot there is an organic shell. So how do we make quantum dots? We use in our lab what is known as the single source precursor method. And so we make uh, uh, complexes, metal complexes, and then we heat them at high temperatures with what is known as a thermolysis reaction, and we can form quantum dots in a flask, or we can make them into films, which is ASEVD, or we can spin coat them, or what is more popular now for scaling up our materials, we use what is known as the melt method, where you just heat it in a furnace and you basically break down your complex to give you your nanomaterial. So when we talk about precursors, we have what is known as dual source or a single source. So if you want to make a metal selenide, metal chalcogenide material, you can take a metal salt, or a chalcogenide sauce. So, so there's examples here. So if you can take metal, tantalum or niobium, and your chalcogenide salt can be something like trimethyl silyl or bis trimethyl silyl uh, complex, and you can heat them up. But you will see that you use very high temperatures. This is 400 to 550 degrees, and there are obviously some drawbacks where the metal alkyl that you starting material is the metal alkyl, and it's very toxic. You're using high temperatures, low air and moisture stability, and there are the problems with pre-reactions in thin film deposition. What we can overcome this by using a complex that already has both the metal and the chalcogenide. So metal chalcogenide bond already present in the molecule. The temperature of decomposition is much lower than for high joule source, and more stable, and it's more flexible. Now, going back to the history, so this was the first route to making cadmium selenide quantum dots, which won the Nobel Prize in 2023. So yeah, they use dimethyl cadmium and triacrylphosphine selenide, or dimethyl cadmium with this bis trimethyl silyl selenium complex, and thermally decompose the two sources in triacrylphosphine oxide to give you what is known as topo-capped cadmium selenide. There are disadvantages, as I mentioned, because the starting material is dimethyl cadmium. There are videos on YouTube that show you how they make this material, but you have to be extra careful in making sure that this dimethyl cadmium does not be exposed to air, because it could explode. And they are very pyrophoric materials and also very toxic. Now, so that reaction, that paper won the Nobel Prize in a few years ago by a group in an MIT, the Bewendi and Brusk combination that gave you cadmium sulfide and cadmium selenide quantum dots. Now, so how can we now bridge the gap between nano and quantum? Obviously, we need to our aim is to design materials and explore their properties for quantum application, and we have to look for suitable properties and synthesize material. So we either make the material and study the applications, or we need to look for the properties uh, and then make materials accordingly, right? So quantum dots are seen as uh, photon emitters, as I've explained. You have they are source of photons, and what is shown in literature that it has a higher optical cross section compared to alternatives such as nanodiamond with the nitrogen vacancy. So there are obviously other sources of photons which uh, researchers use, but what we are trying to uh, promote is the use of quantum dots to give you good quality photons, to be a good quality photon source. And the second part of the lecture by Bertus will give you some indication as to how we are trying to achieve this. And what I've shown you the emission from quantum dots. Those are ensemble material. In other words, many quantum dots that are together that give you the emission. What we are trying to achieve in our research is to look at single quantum dot spectroscopy. So, in other words, emission from a few uh, quantum dots, right? From trying to get the emission that we study the emission from very few particles of quantum dots. So firstly, to make the quantum dots, we use, again, single source precursor method. We use different complexes, and these are the examples. These are for more chemists. And how do we make them? I won't speak about the math method, but the hot injection route is the most popular route to make good quality or high quality quantum dots, where you dissolve your precursor in a solvent and you have a nucleation and growth uh, process, and then you can then collect your material through flocculation and then final dissolution in a suitable solvent. So we have them in uh, solution form, and where we can then study them further. Firstly, before we study them, we characterize them, and X-ray diffraction is one of the techniques. Yeah, we can determine the phase and the purity of the phase, and we always like to, make materials with good phase quality, phase purity, and then we can view them under the microscope, which we have at UniZulu. We have a 25 million rand high resolution electron microscope, and here you see in this figure. This is for cadmium sulfide. You can see very good quality or high quality quantum dots of cadmium sulfide, and then you see the very fine structure on the high resolution electron microscope. These are the lattice fringes, and these are reflections of atoms, and you can see that they're quite pure, almost defect free, which we want, and then we can further characterize them using EDS mapping and selected electron diffraction said. So this is the cadmium selenide, again, similar to the cadmium sulfide. You see very small particles giving you good resolution in terms of lattice fringes, and then the EDS mapping. So we've made those are recently made quantum dots, and you can see the first thing we do is study the optical properties. This is cadmium sulfide, giving you a band edge, and then this is the solventless route, and then the hot injection giving you much lower. You see for cadmium for the solventless route we have 477 nanometers, but for the hot injection we have much smaller particles at 301 nanometers. So you can actually determine the size, which is not very accurate from the equation that I showed you. From the Bras equation, you can determine the size of the material using the absorption max band gap. And this is cadmium selenide, again giving you good, sharp uh, bandage. And then this is for the solventless route, which is much larger. We've made room temperature metal sulfide quantum dots, and this is a whole range. So we can make almost anything that we want. So these are silver sulfide, bismuth sulfide, cadmium sulfide. We would need focusing on cadmium sulfide and selenide now at present, but we can make a whole range of quantum dots. So this is our microscope. This is the Jolt F200, and it gives us good resolution. And you can see the some of the figures that I showed you. It's almost atomic size resolution. So I'd like to end my part of the presentation, and these are my students and collaborators. And I would like to thank you for your attention. Thank you.